Hey everybody, this is Larry. This is day 18 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem. Hope y'all have a great weekend. The contest was a little tough for me, but I mean, at the end of the day, if you can figure it out, it doesn't really matter. You just kind of keep going. Anyway, today's poem is Ken Plays Flowers. You have a long flower bed, and some of them, however, flowers cannot be planted in adjacent pods given flower bed zeros and ones. If n new flowers can be planted in the flower bed. Okay, so n is equal to 1. Okay, but here 2, no good. Okay. I feel like this is exactly, well, maybe not, but it is very similar to the poem that we had before, right? Like from 2 days ago, 3 days ago, something like that. The daily poem there, but the idea here is going to be greedy, right? Because anytime you can place a flower pot, then you should do that. I think that's pretty much all there is, because there's really, especially when it comes to being adjacent and stuff like that, there's really no way to not be greedy, because it doesn't make sense to not be greedy. I think that's the idea. Of course, that's a very sketchy proof. That's not a proof, but that's just how it goes about these things. I get a lot of questions about about how to solve greedy problems and how to figure out it's greedy, how to prove it's greedy, or if greedy is wrong, why is it wrong, right? And the answer to all those questions, to be honest, is I don't have a great answer for it per se. The answer is just to do a lot more problems so that you can kind of build off a base of problems that you can kind of relate to and kind of use, like, figure out these properties, and sometimes even like messing up a lot to kind of figure it out. I have done that, so and even now I'm wrong a lot often, to be honest. So it is something that you just have to kind of get a feel for. It is mathematically speaking, there are a couple of ways to do it, but I find those really hard. Sometimes it's just by stuff that you learn in grade school or whatever, like proof by contradiction or something like that, or induction or something. But beyond those techniques, which sometimes still is easier said than done, even then, I have no idea, or not no idea, but but these are the things that I would talk about for most poems. Anyway, so yeah, let's get started. Let's try. So yeah, so. So right now I'm just thinking about how to do it in constant space. You can do it in linear space very easily and if you're modifying the input, that's still linear space if you ask me. But and you can, very easy, you just have to keep track of the last element, and that's pretty much it, right? So yeah, so count is equal to 0. It's not that bad. I know that historically I've been very lazy, or not very lazy, but I'm often very lazy on these things, but but for today, I'll try a little bit more, right? So yeah, so if flower bed of I minus 1, and of course you have to check bounds, if this is equal to 1, then this is no good, or previous being a variable that we do, previous is equal to 4, say. Then we continue, right? Yeah. If I plus 1 is less than n, and flower bed of I plus 1 is equal to 1, I guess I didn't need parentheses, but whatever, continue. Otherwise, let's print a flower. Previous is equal to true. And that's pretty much it, except for I think now, this goes to the next state. I think we have to set something to previous is equal to false. Where would I like to do it? I guess if we don't plant a flower, then it's going to be equal to false, right? Oh, well, I guess yeah. I mean, this one, it doesn't matter because in the next spot we're not going to place it anyway. And I think I forgot one case where if flower bed I is equal to 1, then we just continue because, you know. And technically what we said previous is equal to false, but then, you know, I minus 1 for the next one is going to be 1 anyway. So yeah, yeah, is this sufficient? Am I right? And then just return count to the target. This is, I mean, so if you do it in linear time, this is pretty straightforward. Oh, sorry, linear space, this is straightforward. But I'm trying to think whether these are all the states that I need for to in constant space, right? So yeah, let's give it a spin at least. Hopefully, if I'm wrong, hopefully there's gives me a wrong answer very quickly. I don't know that these are all. Let me think about this for a second. Yeah, so we just move on to the next one. Technically, this is false. And of course, these you can probably put them all together, but it's an or statement. But I find this slightly easier though, except for now we have to make this previous thing. So it's a little bit awkward, not gonna lie. But yeah, all right, let's give it a submit. We'll see. I probably did it the other way. This one's more sketch, but turns out to be okay, even though it is slower than I did previously. I think I probably did it the linear space one and previously. See, I mean, I have the same idea except for I set it to 1. And this is exactly the same thing we're trying to do here. This is that's very funky, but yeah, I set the far better is equal to 1, and that's basically what we're trying to do without actually doing that. With our current code, it's going to be linear time because we go through the loop once, and of course it's constant space because we only have 1, 2, 3. Oh, whoops, how did that happen? Like 3 variables or something, right? So yeah, this is a pretty simple one only because it's easy, and your intuition it matches that of greedy. Greedy isn't always greedy sometimes could be intuitive but be wrong, right? So it's not always the answer, but in this one it's easy in that sense. But if you really want to prove it, maybe it's a little bit trickier to say or to actually prove like in a stricter way. But yeah, that's all I have for this one. Stay good, stay healthy, to good mental health. I'll see you later. Bye bye.